was. But I'll be talking about quantum graphs. That's sort of some of the theme of this week. Makoto talked about them yesterday. Ludmilla and Yvonne and Jason are going to be talking about them on Thursday as well. Given what they're going to be talking about, or the sort of flavor of it that they're going to be talking about, and the flavor that Makoto was talking about yesterday, I figured it would be a good idea to talk a bit about quantum graphs in the sense of Nick Weaver. So thinking of them as certain quantum relations. And so I'll recap maybe a bit of that, where that might come from, what that might be good for, and we'll look at what homomorphisms between those look like. And that's also going to be a bit of a precursor to Yvonne, Ludmilla, and Jason's talk on Thursday. Okay. Yeah, and please interrupt if you have questions. I mean, I'd really like this not to just be me talking for 2 hours. That's, that might be exciting for me, but I'm going to guess it'll be less exciting for you. Okay. So what's a vantage point by which we can actually get at these things? And I know Yvonne gave a talk about this at some point during this workshop, but I wasn't here for that, so I don't remember what he said by default. But let's say we've got some sort of map N, which is really N is standing for noisy. So this is a noisy channel. And this could be something as simple as you're going to the drive-through to order your, takeout meal or whatever, and the intercom is really bad at the drive-through, and so they mix up your order because they can't hear it properly. And so there's this idea that there are certain orders that can be confused with each other, right? Or certain, maybe if you want to add on the name of the person that's making the order. Well, I say my name is Samuel and they hear Daniel. That's happened to me many times. And so you want to kind of keep track of what can be confused with each other. And when we talk about a channel in information theory or in quantum information theory, you can really think of it as a completely positive trace preserving map. And since I'm really thinking of this in a classical context, really this is like some sort of, you know what? All right, I'm going to regret that. Some sort of map on, diagonal matrices. So here, dx is just the set of diagonal matrices over, matrix algebra of correct size. This is completely positive and trace preserving. And, if you write down what that is, let's say on a diagonal matrix element, or matrix unit, you're getting some sort of sum of, these diagonal guys, but then you have some sort of weights and they've got to be positive. And in some sense, we can, act like this is essentially the probability that, when you give the order X, that they're actually, getting the order Y as what they're hearing, sort of thing. And in this context, then, how would you say that, two orders can be confused? Well, you just say they can be confused if they can both be associated with one of these things at the same time. So we'll say x1 and x2 can be confused if there's some y that sort of links them together. So if there's some y such that this product of probabilities is not zero, right? So you put in your order x1 and they might hear it as y, or if you put in your order x2 and they might hear it as y as well. And so there's a potential that you get the wrong thing in the end, right? That's really what we mean by things being confused. Of course, I guess in this context, like it's probably the case that an order can be confused with itself, which maybe you care for or maybe you don't, right? And that's really the, in some sense, whether you care about that or whether you don't care about that probably relates to whether you care about having graphs with a loop at every single vertex or whether you don't want that. And for pretty much everything that we're talking about today, that doesn't matter. It's just a cosmetic thing. except for one thing that I'm not quite sure how it works, but anyway. So you get some sort of graph from this, right? And this is really the confusability graph. Right, and it's got vertex set x, and you say the two things are adjacent if they can be confused, and again, depending on your context, that might mean you have a loop at each vertex, and it might not, and I'm not really gonna worry too much about that. But there's actually something in the background here that's, really this confusability graph, I mean, it's evident from this, it's coming from the actual noisy channel, but there's actually another way to see that it comes from the channel, and this is something I sort of want to use as motivation. So you got this, channel N, but it actually has, it probably has many, but some sort of Choi-Krauss representation. It's a completely positive trace preserving map, and so you can decompose it in a certain way so that n acting on something looks like a sum of products of the following form, like fi. I always put the star in the wrong place. Let's put it on the other side. That's more exciting. Like that. Where these FIs are, I guess, some sort of rectangular matrices in the correct spot to make the dimensions work. And I guess there's finitely many of them. And actually, you can give an upper bound on exactly how, well, at least an upper bound on how many there are. The question of how few you can choose, that's not something I'm really going to worry about today, although that is a very interesting thing. And the other thing that happens is that the sum of these Hermitian squares going the other way, so Fi star Fi is the identity, and that's really capturing that this is a trace preserving map. And of course, each piece in here is completely positive, so the sum is completely positive as well. And that's all well and good, but there are lots of possible choices for these FIs. And I really have no sense as to, how many choices there are. There's lots. But one thing you do get is that you get this operator system. Shoot, is that the way I want it? Oh, it's probably the other way. Yeah. Dang. Okay. Yeah, okay, so you get, if you take these spans of these products of Fi star and Fj, this is, something inside of matrices of size x, whatever x is. But this is actually an operator system. And again, all that means is that the identity belongs to this, which is clear by just taking the Fi star Fis and summing them up, right? That's why I need it the other way. And it's closed under the adjoint, taking the conjugate transpose. So this is a nice operator system. And the thing that's very nice about this is this operator system is independent of which Choi-Krauss operator sort of representation that we chose. Because there are lots of choices of Choi-Krauss operators, but the operator system you get for your noisy channel is still the same. So that's actually quite nice. And then, yeah.
Now work on MX or still on DX?
Right, yeah, so it's still on DX, but the operator system you get won't necessarily be in DX. And actually, I mean, it turns out to be very boring if it was in DX, because it turns out, in this case, this operator system is also keeping track of exactly what gets confused, right? And so if it's only in DX, then that's basically telling you that nothing gets confused, and you have a perfect channel, so you don't have a problem to solve. or you get a perfect takeout order and, you know, your day is nice. I don't know. Yeah, so yeah, this thing is sometimes called the operator system of the channel, S sub n. But it turns out that, you know, in this setting, S sub n is actually exactly going to be the operator system of this graph. Just in case, the operator system of the graph is it's spanned by a bunch of matrix units, and you take the ones where, and again, this first part is either cosmetic or not, but most of the time it's cosmetic. So you take all the diagonal matrix units or the ones where xy is an edge. It's a horrendous bracket, but anyway, there we are. And that's your graph operator system. It keeps track of exactly what's adjacent, and it turns out that the operator system of the channel matches with your operator system of your confusability graph in this case. Right. Yeah, so we got this kind of nice unique thing regardless of what Choi-Krauss representation that we had. And then maybe I'll say one more thing about this S sub G or S sub N, whatever you want to call it. This is oh geez, I guess X is my vertex set. Okay, well, it's my own fault. It's a dx bimodule. So if you pre or post multiply any element of SG by an element of the diagonal, then you're, you know, especially from this description, you're clearly still back inside the graph operator system. So it's a bit of extra structure, which, you know, again, depending on what flavor of quantum graphs you look at, sometimes you care about that structure and sometimes you don't, and that's okay. Today we will care about that structure. Yeah, the idea here is, I mean, we've done all this with a classical channel, and you know, it kind of begs the question, well, why not do it with quantum channels as well, right? It turns out you got some similar things. Yeah.
Do you prove the statement that the Sn is independent of the choice of the operators by showing that it's equal to the other thing?
Yeah. So actually, yeah, that's a good point that you're making right there. So it turns out like this is a special case of a more general fact, which is that basically you can do the exact same thing, but you can replace this classical channel, which, you know, goes from diagonal to diagonal, with a quantum channel. Yeah, and then it still is true. Yeah, and then it kind of happens to be the case in the classical setting. And I'm sorry, I'm pointing at Vern because it's in it's in notes of his from you know, entanglement non-locality notes. But in the classical case, it turns out to match up exactly with the confusability graph. Yeah. Yeah, so it's really nice. Yeah, any other questions so far? Okay, no? That's good. Please interrupt me, that's good. Okay, let me erase the title. Hope we're okay with that. All right, so this, you know, from this classical channel, we got a classical graph. Of course, we had some extra structure with it, but, you know, that's all fun stuff. But you can actually do the same idea with, you know, with a quantum channel, right? So, and the only difference between a classical channel and a quantum channel is essentially your domain and codomain. It's still a completely positive trace preserving map, right? But now it's getting, you know, maybe more complicated. We'll use a more complicated letter. So we go from a matrix algebra to a matrix algebra. This is CPTP. Right, and again, there's the Choi-Krauss representation. Well, there's a Choi-Krauss representation. There are many of them, right? And so you can do the same thing again, right? You can you can write this as some sum of fi stuff, fi stars. Oops, no, that's wrong. Sum I equals 1 to k, and I think actually you can arrange in this case for k to be less than n times m, if I remember correctly, something like that. Anyway, and as before, these fi star, or fi, yeah, okay, there we go. Fi star fi's, these things actually sum up to the identity in the correct space. And again, these fi's are rectangular of the right size, so that when you have, I guess, an n by n matrix in here, you end up with n by n matrix in this piece of the sum, right? Okay. And then in this case, so, you know, as was asked earlier, this, you get some sort of operator system spanned by these fi fj stars. And again, this is independent of, you know, yeah? Oh, I did it again. That's a good indicator for today, isn't it? Okay, fi star fj. So independent of our Choi cross representation, right? You get some sort of nice, yeah. Yeah, I think some references put the star on the other side for, yeah.
They want this to be unit also.
Yes, yeah. There's some order that makes it work. That's what matters. Yeah, so you get some sort of nice operator system from this in the same way as before. And, you know, actually one interesting question that Vern was reminding me of yesterday is that we kind of, there's a lot we don't really know about these systems that we get in the sense, like, so here's, I know we often reserve questions for the, or, you know, sort of open questions for the end, but I'll flip it around and give one right now. Okay, so if you have, let's say you have two channels, right? So phi and capital psi, right? These are quantum channels on the, you know, same sort of, like, let's even assume they're both from Mn into Mm, and let's not even just assume that their operator systems are, you know, completely order isomorphic, but let's actually assume they're equal. So the spans are exactly the same. What can you say about the two quantum channels? And as far as I know, this is still pretty wide open as to what could happen. Yeah, but it's definitely something that would be, you know, good to know or understand, even in like particular cases, like when the, you know, operator system of the quantum channel is maybe like a full matrix algebra or something like that. What, you know, what can you say then? Yeah, but anyway, that's sort of a side note. I don't really have a good sense of how to attack this problem, but it is one that should be attacked nonetheless at some point, you know? Yeah, okay. But what I want to do with these, you know, operator systems of a quantum channel is I want to actually use them to sort of, you know, in the classical case, it lent itself to a nice classical graph. In the quantum case, we wanted to sort of lend itself to a quantum graph, right? Okay.
Complex combinations keep having the same
Sorry, say that again?
Operator system. Do convex combinations keep having the same base? Well, is that too much to ask? You have like t pi plus 1 minus t psi, which is CPTP.
Right.
Take the span, so it seems to be the case. You could just write explicitly
but you can start to observe compounds.
Yeah, that's like, I actually don't know, because yeah, when you start writing down your Choi cross operators, well, I'm not exactly sure what. Yeah.
I don't know. The intuition would be probably no, because so this thing it would resolve the zero error capacity, and mixed channels capacity usually decrease.
Right. Yeah. Okay.
You have two nice channels in stream. Here's an example. You have perfect channels.
Yeah.
You mix them.
Okay.
You can have some permutations.
Okay. Okay. That's good. I appreciate that. Okay. And I just realized that I actually have a second board. I'm sorry, I'm really not used to using these boards, so I'll try to stop erasing the same board. I'm sure everyone's thrilled about that. Okay. So this is the good thing to think about. It's not the topic that I'm talking about today, but it's good to think about. We're going to talk about quantum graphs. We're going to do it in the sense of keeping track of some sort of operator system, right? So again, you can think of this operator system as like keeping track of essentially like what quantum states can be. Yeah.
Back to this question.
Yeah.
Say something, it will have one-sided inclusion.
Oh, interesting. So like if you had SV contained in S psi, I don't know.
Do we know anything if we have, if you choose psi to be composition, so phi composed with phi?
Oh,
That should be true. I think it's because the computability.
It just tells you that the operator system, the composition is the image of the first operator system under the second map. Give you
yeah.
paper of Nilanjan Nadada and Isner Rahman students specifically asked this question in case when the span is the full matrix algebra. They prove some things about such quantum channels, and they don't know what the relation is between the quantum channels.
Yeah.
So let me ask another question. So
Sure.
suppose that you have an operator system in matrices. Is there kind of a nice way of writing the channel for which this our operator system is defined?
It's in Dumont Severine Winter's paper. In my course notes, give a different way to do it.
Yeah.
So it's not unique, but okay, there is a nice way.
Every time you fix, you take a basis, I think you can hook up a channel basis.
Yeah. Yeah, so in theory, there are probably there could be many ways to do it. But again, it still gets to the same question of like, okay, you have all these potential ways to build this operator system of your channel. Well, how are those channels actually related to each other, right? I don't know. So anyway, very interesting. Okay. Good. So what we want to do is we're going to keep track of this operator system, but then I'm also going to do something similar to what Makoto was doing yesterday. I want to essentially keep track of the vertices in some sets. So we're really keeping track of two things, right? So we keep track of the operator system, but also the possibly quantum vertex set. And really all I mean by quantum set, because when someone talks about a quantum set, they often are talking about some sort of finite dimensional C-star algebra, so a bunch of matrix blocks. But then as Makoto was mentioning yesterday, you sometimes need to actually have some sort of measure type thing on that as well in order to do things properly. So some sort of delta form. And that part I'm going to sort of kind of ignore today, even though it's still kind of there, but I kind of don't need it for today anyway. Okay, and let me, so if you just wanted to keep track of this operator system coming from your channel, that gives you some form of confusability, and that's perfectly fine. And that relates closely to, I guess, what are known in the literature as non-commutative graphs, and that's going back to some of this work of Duan, Severini, and Winter, and then also Dan Stalkey. What I also want to, if I want to keep track of the quantum vertex set, then I need a little bit more structure imposed. And so one thing I want to just recall from a long time ago, as in yesterday, so depending on your framework, like if you're looking at your quantum graph using this version of adjacency matrix, right, which we talked about yesterday, the adjacency matrix if you start in that framework, it gives rise to an operator system, S, but it's not just an operator system, it's also a bimodule over the commutant of your quantum vertex set. And that's really what I want to focus on. So it's a M prime bimodule. So it's just closed under pre or post multiplying by elements of the commutant of M. So M is our quantum vertex set. So it's just some finite dimensional C-star algebra. In fact, I'll probably in general just refer to it as a finite dimensional von Neumann algebra, just to needlessly beef it up, even though it's the same thing. But, okay. The last time I'll erase for a while. Just yell at me if I don't change boards. So a quantum graph in the sense of Nick Weaver, what it really is you have essentially a triple, although actually the third part kind of doesn't matter. We have a triple. You have three things, S, M, and Mn. And in good fashion, I'm not defining the first thing first. So M is some sort of finite dimensional von Neumann algebra or C-star algebra. Really, it's just a isomorphic to a direct sum of matrix blocks. And then S, right, is an operator system, but it's also an M prime bimodule. Okay. And another way to think of this is that, so I mean, in Weaver's work, he talks about quantized versions of relations, right? So like, what does it mean? You look at like, what does it really mean for a relation to be symmetric or reflexive or transitive, and then trying to translate those things over to a quantum relation. And so in that sort of language, you have a a reflexive symmetric quantum relation is essentially what this is, right? I wanted to make sure I got the right words in. Okay. And again, reflexive and symmetric being the two parts of the sort of relation, right? Your relation that really is built into the background for a classical graph is that two vertices are related if they're either equal or adjacent, right? So that's certainly reflexive and symmetric. And the reflexive part, again, depending on whose paper you're looking at or what exactly you want to do, that's something you might keep for convenience or you might throw it away for convenience. Anyway. And then, no. Oh, this is a lot more than I thought. Okay. Okay, that's going to be exciting. All right. So as an example, is this too low or is this okay? Yeah, okay. So if you have a classical graph, right? So just vertices and edges, right? And then I guess essentially, kind of, you can think of it like having a loop at every vertex, I guess. But then if you take this graph operator system that we talked about before, and you take the diagonal subalgebra of matrices over your vertex set, and then matrices of the same size as your vertex set of G, then that's your way to think of a classical graph as a quantum graph in this Nick-Weaver approach. Okay. Yeah. All right. And then I should mention, because this looks like horribly embedding dependent based on how we've written it right here. Like it looks like it depends on how you chose the embedding of your von Neumann algebra into MN, and in some sense it doesn't. So this thing doesn't really depend on your choice of embedding, and what that really means is that like if you came up with another embedding of M into another matrix algebra, then there is a corresponding operator system that is an M prime bimodule. And then pretty much all the things that we're doing, they sort of transfer over in a natural way. However, when you're actually writing down some sort of like operational interpretation, it kind of helps to have an actual realization of M inside of a certain matrix algebra. Okay. All right. How are we doing? Any questions? Are we feeling okay? Yeah. Okay. All right. Okay. So one thing I want to talk about from the this quantum graphs perspective, and then I think in my title I mentioned something about eventually going to quantum colorings of quantum graphs, and we'll eventually get there. But there is one piece of information that I want to talk about before getting to homomorphisms at all, and that's this idea of that's this idea of connecting states. And so this is sort of getting back at what actually gets confused by your quantum channel, right? So again, using this Duan-Severini-Winter sort of construction, or whichever construction you wish, you've got this operator system, and it arises from some sort of quantum channel, right? So it's really, again, describing confusability in some context. And then you can talk about, well, what exactly gets confused, and one way to talk about that is connecting states. And so this is right out of Weaver's paper, but let's say you have two, let's say mixed states. You can do it for pure states as well, but A and B. So these are, you can really think of these as density matrices in your matrix algebra. So they're positive semi-definite. Their unnormalized trace is 1. And we'll say that these are connected by S. If essentially, all right, if essentially this inner product with respect to, Hilbert-Schmidt inner product is non-zero for at least one x in our operator system, okay? And I guess, yeah, I'll probably try to have linearity on the right for my inner products, but that will probably accidentally change in, half an hour just for annoying reasons. But this is essentially getting at the idea that you can, confuse these mixed states A and B in some sort of way, right? So this is really tracking what you can confuse. And then what might be nice is like if you have, so if you have like let's say you have two operator systems, right? So, and you've got some sort of, let's do, okay. Let's say we've got like some sort of quantum channel, right? Going from one matrix algebra to another. And then you want to see what happens to, or like is, and let's say you've got some sort of, operator system in S, and then an operator system in, operator system S in MN and an operator system T in MM, and you want to see like, well, is there any sort of correspondence to what gets confused in one place versus another, using this quantum channel. Hang on, that's not what I want. Okay, I'm sorry. There, kill that last line. All right. You want to see if there is an operator system in the codomain that essentially perfectly tracks like how things are confused along phi with respect to how they were confused initially, right? Okay, so here, I'm gonna have to consult this or I'm gonna write this down wrong. Too many quantifiers for this time in the morning. So is there an operator system, right? T such that the following happens. So I'm going to try and put it in a bracket, but let's say such that T connects two states A and B. That happens if and only if S connects two corresponding states in the domain. Now, the problem is phi is not invertible, so you can't, it's not the right thing to write down the inverse, but because this is a map going from MN to MM, you kind of have this advantage that you have the, the Hilbert space adjoint of the CP-TP map, phi star, and that's a unital completely positive map going the other way. And so then really what you're looking for is you want something that connects phi star of A and phi star of B. Like, is there some sort of operator system inside of the codomain that does that for you?
These are not anymore states, but it doesn't matter.
Sorry, say that again?
Phi star of A and phi star of B are not anymore states, but I don't think that's a problem, right?
Yeah, ooh, that's a good point. I don't believe it does matter, but yeah, that's a good point. Yeah, they don't necessarily have to be densities, even if A and B are, right? So, yeah. Okay.
I got slightly confused at this point. So we've used the trace on MN and MN, turn them into Hilbert spaces.
Yes.
And then this is the Hilbert space adjoint.
Yes. Yeah. Yeah, not to be confused with the Banach space adjoint. Yeah. Which unfortunately we have the same notation for, so that's really helpful. Okay. So the answer is actually yes. There is something that does this. And it kind of relates to these Krauss operators before, which is quite nice. And I'm sure I wrote them down wrong in my notes just as before. Yes, I did. Okay. So in this case, the T that does this for you is I think I have the star on the right side now. It's basically you take anything in S and look at these Fi star Fj's and then take the span of all of those. And this is this is for your particular Choi-Krauss representation of your quantum channel phi. But again, and kind of magically, this doesn't actually depend on the choice of Choi-Krauss operators. You still get the same operator system, which is kind of magical. And this thing is okay. This is often referred to as the push forward. So the push forward of S along the quantum channel phi. And the reason I mention that is because when you start talking about homomorphisms and quantum homomorphisms of these kinds of quantum graphs, push forwards start showing up all over the place. Oh, are you?
J is meant to be
Yeah, they're okay. Yeah, they're rectangular, but basically they're your Krauss operators for phi, right?
But then, don't you get the operator system in Mn, that domain from phi? I mean, phi b.
Oh, yeah. I apologize. There we go.
How different it is just from the image of particle S?
Oh, it's like, yeah, okay. So it contains the image of S because you can look at the case when I and J are the same and add it up, right? And then you get S, but this potentially gets more stuff. Yeah. Yeah, it probably does. I don't have an example offhand, but yeah.
How do we have a trade-off if you define it? Is that something?
Sorry, say that again?
Do we have trade-off operator, identity operator in T if you define it this way?
Oh, shoot.
I think you just had
Right,
the
just a
dimensions
CDP.
messed up at first. I think the S was supposed to be an MM, and
That's probably,
your stars were in the right order. I think your N's and your M's over here were backwards.
oh, yeah, okay. Yeah. Hmm.
Yeah, the stars go the other way.
I think this is the point where you don't want the unit. You're not claiming this quantum graph.
Ah, yes. Yeah. Here,
Well, okay, so
how would I fix this? Yeah. There, is that better? Self-adjoint subspace. Yeah. Yeah, that's a good point. And actually, I mean, even in all the results I'll talk about today, I don't actually care about exactly what the push forward is. I really care about where it is, where it's living. So yeah, that's a good point. Whew, my apologies. Yeah. All right. Okay.
Is this understood what happens if you replace traces by states as your reference?
That is a good question. So like, okay, so let me just make sure I understand what you mean. Like when you're replacing traces, are you talking about right here? Or are you?
I'm replacing traces on a man by reference state, say faithful state.
Oh, okay, so now you're looking at.
I have a new scalar product, I have a new notion of what it means.
I see, I see.
I have a new phi star.
That sounds very interesting. Unfortunately, I also, yeah, I have no idea, but yeah, that sounds really neat. Yeah. Okay. Well, let me say then, you know, okay, so having this idea of push forward, what should we sort of think of as a like homomorphism from one of these quantum graphs to another one? Just to sort of go along a similar line to, oh, right, I got to push this one up too. To go along a similar line to what Makoto was talking about yesterday. Okay. All right. Okay. Yeah, so what a homomorphism should look like. And then we'll talk about, you know, quantum versions eventually. Okay, so in this case, okay, so now this T I'm about to write down is not necessarily that anymore, but let's say you have, you know, two quantum graphs, right? So S, and then your quantum vertex set is given by this finite dimensional C star algebra M. And then this other one where you have T as your operator system and this some sort of finite dimensional von Neumann algebra N. And then I don't know why I have N and M here. Anyway, that's not the point. and you want to talk about what it means to have a homomorphism from one to the other, morally, it should be a quantum channel, right? So you have some sort of quantum channel going from this matrix algebra to this one, right? And then if you write down a Choi-Krauss representation, and it shouldn't matter which one, but let's write one down anyway. Then essentially what you should get is that the push forward of S along this quantum channel, it probably won't be all of T, but you want it to be contained in there, right? And that's essentially the idea. So whether you write it as span or each individual piece is contained in T doesn't really matter. But anyway, this thing should be contained in T. And there's one other piece, if we really want to, so again, you might agree with this or disagree with this, but if we really want to sort of keep track of preserving structure, then we should probably have some sort of way that it interacts with the quantum vertex set as well. And again, if you don't want to have that, that's fine, but I will. And so I'm going to sort of stipulate that if we do the same thing on, not on M, but on the commutant, then we want this to be contained in the commutant of the von Neumann algebra on the other side. And this is, so this M prime here, because S is M prime bimodule, and it's unital, it's already got M prime sitting inside of it, right? And so this second push forward, it's at least already going to, if we have this first condition, it's already going to be inside of T. And T contains N prime anyway. So this is just asking for a little bit more. It's just asking that it actually gets pushed into N prime instead. And so, when Mike Brannon and Priyanka Ganesan and I were, looking at these things and trying to look at quantum chromatic numbers of these, this second condition invariably started coming up. It seemed to be natural and extremely convenient to impose. Yeah. Okay. Yeah. Any questions so far? Good. All right. Okay. So then, of course, you could talk about, well, what would, because we haven't had enough quantum yet, let's say, well, what would quantum versions of this be? All right, and maybe now you've got some sort of, some sort of push forward where, maybe you've got some sort of extra piece, right? Something like that. Like maybe this is supposed to go into T. And it turns out, what we get is a little bit more restricted than this, but maybe it should look something like this. And this extra one here is really the identity operator on, in some sort of ancilla sort of von Neumann algebra sitting in the background. And that's really where the quantum part comes in, right? So if that part is just the scalars, then ideally you should be getting the same thing as before. But of course, you could look at well, maybe it's a nice matrix algebra, right? Or maybe it's everyone's favorite ultra power of some hyperfinite 2-1 factor, right? Or maybe it's just some general tracial von Neumann algebra, and you could look at those different sort of genres of quantum homomorphism, much like one might do with non-local games. Yeah. Yeah, so that's where I want to go. The problem with everything that I'm about to, or everything that I just said though, is that like if you want to try to cast this in terms of non-local games, you run into a bit of an issue right away. And this is something that, again, Yvonne and Ludmilla and Jason are going to talk about on Thursday. But at least for homomorphisms from one classical graph to another one, when you formulate a non-local game for graph homomorphism, that's a graph or a game with classical questions and classical answers, right? And it's a very well-studied game. There's still a lot we don't know about it, but it's also very well studied. Both of those things can be true. The problem is then when you start incorporating quantum graphs, well, you're probably not going to be able to do it with classical questions and classical answers anymore. You probably need some form of quantum questions and quantum answers. And so to make it simpler, also because with this formalism, it's kind of hairy as to what exactly happens in the general case. We're going to assume that we're starting with a quantum graph and we're ending with a classical graph. So we're going to assume that this target graph, which I guess I'm calling T and M, this thing is actually classical. And all I mean by classical is that T is the graph operator system of some graph, and then N is the diagonal subalgebra, and sitting inside of MM, and M is the number of vertices on this classical graph. Okay, and then that'll get us to look at like games where we have quantum questions and classical answers. And it'll serve as a nice sort of precursor to, or at least I think, a nice precursor to what you'll be talking about on Thursday. Yeah. Okay. I know we're going 2 hours. How do you guys feel? Do we need a break at this point in time? Are we feeling okay? Or? I can decide. Wow. I'm not used to that. Okay, this is probably a natural point to take a break because we're going to get into how games look in a second and stuff.
10 minutes?
Sure, let's do 10 minutes. Yeah.
After some talk, we want to think a bit about how to continue on Thursday, possibly, whatever for we can.
Those are discussions on discussion.
Yeah, good.
We're going to be battered in 15 minutes.
yeah, anyway. Sorry, I had my mute button on and now it's not. Yeah. Okay, so yeah, we ended here. Okay, so welcome back. So with all this in hand, we want to essentially try to cast this like homomorphism, quantum homomorphism thing as some sort of non-local game. And since that's going to involve, at the very least, quantum questions or answers, we're imposing a classical target graph. So that means we're going to have classical answers, but we still have quantum questions. How many of you are familiar with quantum question, classical answer, non-local games? All right, so 1 or 2 or 3. I think Yvonne and Lumil just didn't want to raise their hands, but so I can go over those a bit. That's okay, that's good. I wanted to double check first. Okay. So to start this, so we're looking at, sometimes these are called quantum to classical games. And these have shown up several times in the literature. So one classic example of it is Oded Regev and Tomas Vidic have a paper, I think it was from 2015, on quantum XOR games. And these are XOR games where your questions are not quantum questions. And I might say something more about those in a few minutes, but for these games, I mean, it might actually help to look at the operational sort of picture first before, because one unfortunate thing that happens when you start imposing quantum questions or quantum answers or both is that when you start trying to keep track of the data that's required, indices start flying, right? And so it helps to see an operational interpretation first. And fortunately, the picture is the exact same with one key twist. So you've got your referee, right? So in our typical 2-player, 1-round non-local game, we have our 2 players, Alice and Bob. They are space-like separated. And normally, the referee is sending each of them a classical question, right? And then they think about it for hem and haw for a while, and they come up with some sort of classical answers, A and B, right? And then they win based on some sort of rule function. Okay. The problem here is if we have quantum questions, what is the referee actually sending, right? So what does the referee actually send? Okay. And the thing is, so if your question set is size n, right? So in a classical game, you'd be, sending some sort of pair of questions, x to Alice and y to Bob, right? And this would be, the set of 1 up to n squared. But in the quantum setting, you might not actually be doing that. So not necessarily this. But the way to think of it is that these really correspond to certain, nice, pure, like tensor product states in certain register spaces. Okay, so instead of looking at this, you look at some sort of state in Cn, tensor Cn. Okay, and the n is still getting at the idea of the size of your question set. But instead of sending a question pair, you're actually sending some sort of state. And to get at the idea of sending this to Alice and Bob, really it's like the referee sends the first piece to Alice and the second piece to Bob. Or another way to think of it, if you don't like that, is that Alice and Bob have their shared entanglement space or whatever that's going to look like, but then Alice also has access to question space and is receiving this from the referee, and Bob has access to a question space and is receiving this from the referee. But those 2 spaces are potentially entangled, right? So that's.
Busy confusing anything. Let me just check. So this is a warm one.
Yeah, just a unit vector. That's right. Yeah, although you can if you want, but I'm trying to keep it simplified. Yeah. So, okay, so yeah, we're going to keep this as a unit vector, okay? But there are some sources that will instead look at it with densities, where, so instead of phi, you'd have like phi star would be like an example of a sort of question, but maybe it's like a mixed state instead of a pure state, right? And then you can think of it as, okay, the referee has sent that mixed state to the two players, like each of them have the access to their piece, and they're doing some sort of quantum operation, right, to come up with their answers and give them to the referee.
When we talk about piece, we're not assuming this is a simple tensor.
No, it may not be a simple tensor. It might, and in fact, in the interesting examples, like the interesting examples, usually this is like some sort of maximally entangled Bell state. Yeah, but it captures this setting, right? Because this setting, a classical question, really looks like, right, tensor product of EX and EY. And we're just allowing some sort of weird like quantum mixture or something like that, right? Yeah. Okay. All right. So what do we really have going on here? Oh, geez, that went higher than I thought. Okay. So what we actually have, if you think about what Alice and Bob actually have access to, you get a sort of triple, and it could be more depending on what their shared entanglement space looks like, right? Their resource space. So really, you have some sort of copy of CN, and this is Alice's copy. You have maybe, depending on what kind of strategy they're using, they might have some sort of shared resource space, H. And then there's another copy of CN, and essentially what's happening is that Alice has access to these two, and Bob has access to these two, right? And what they're going to do when they receive this state as their quantum question, they're going to do a measurement, okay? So they're going to do some sort of measurement on their portion of the space. So it's like running an experiment, and then the answer, they're going to get some sort of classical answer with a certain probability, and they're going to report that to the referee, okay? So Alice measures, right? And this is using a measurement system on the two pieces to which she has access, so CN and H. And this is going to mean, so this may look a little weird at first, but this is actually, there's only one measurement system, which might look wrong because in the classical case, you have lots of measurements, right? But if you sort of inflate it in the right way, then it actually is just one measurement system. But she measures on CN tensor H, so you have some sort of collection of operators, P sub A, how many answers do I want? Let's say M. And this is some sort of POVM, positive operator value measure. And it's in the bounded operators on CN tensor H, okay? And then Bob has the same thing, but now it's on H tensor CN. So Bob also measures, right? So you got some sort of POVM, a bunch of QBs. Yeah, POVM. Gotta make sure the tensors are in the right order. Okay, and then because you know, in the same sort of way that this comes up in non-local games, right? So the order in which Alice does individual measurements might matter, and the order in which Bob does individual measurements might matter, but whether Alice measures first or Bob measures first should not matter, right? And so then if you write that down, what that actually means is, I'm not going to squat that low, so what that actually means is that tensoring on identities on the parts where they don't actually act, you get some sort of commutativity requirement. So PA, you got a tensor on an identity on the right, and then QB, you got a tensor on an identity on the left. And this has to be 0 for all A and B. These things have to commute. Okay. And maybe I should just mention before we actually get to, you know, what are they answering with what probability, it turns out that, this is not too hard to show, these two things commuting actually means that, like, so if you think of PA and QB, they're each bounded operators on C to the n tensor H or H tensor C to the n, okay. But that really means you can think of it as an n by n matrix whose blocks are in B of H, right? Okay, so if you write down those blocks, I did warn about indices, so I apologize. But you know, you've got piece of A, and then you've got index I and J for your which block index you're looking at. And then Q, you've got the same thing, and okay, I can't use the same letters, so K and L. Well, all of these have to commute. That's the exact same thing as asking this. This is for all, let's see, for all A and B, I guess those are between 1 and n. That's the number of answers I have. And I, J, K, and L are all between 1 and n, because that's the size of the matrices that I'll get is n, because that was my question size from before. Okay, so that's actually quite nice. You still have this sort of like commuting operator framework that we're used to in non-local games with classical questions and classical answers. Okay, and then how does it actually, like, how does it work? What do they answer with? Well, depending on this joint measurement, they're each going to get an outcome A and B respectively, and that's what they're going to answer to the referee. But then what is the probability that that actually happens, right? So for lack of a better way to write it, let's say it's, you know, P of AB given that they received the unit vector B. And this is essentially, let's see, so you've got Alice's POVM, or positive operator, pardon me, Bob's positive operator, but they've got to have the right identities tensored on for this to actually make sense. And then, you know, we're assuming they have some sort of prepared entangled state, chi, or maybe psi would have been better, but anyway, here we are. And then the problem is that, you know, the phi, like if you think of how this actually works, phi is on the first and third factors, and chi is on the second one, and no one wants to actually, you know, write that down carefully. So we'll just act like after a flip, this is really phi, here, I'll put a dot tensor just to remind you that this is not quite right. Phi dot chi, and then inner product of that with itself. There. So that's your probability right there, that they actually give those two answers. Okay. Of course, yeah, with the correct flip to actually make sure those are on the right spaces. Okay. Yeah, of course.
So you've set n equals n and m equals m, but it's a mild generalization that we could sort of let Alice and Bob have different sizes.
Absolutely, yeah, they could have different questions. So yeah, this could be like CN1 tensor CN2, and that would be like the case, you know, when you have a non-local game where the two players have different question set sizes, like the non-synchronous version of like the linear constraint system game would be an example of that. Yeah.
This depends on chi, no? Why do you say that the question is just phi?
Sorry, you're saying it depends on chi, and the only reason it depends on chi is because that sort of dictates part of the strategy.
Depend on chi, right?
Yeah.
Chi is part of their strategy.
Yeah, it's part of their strategy. So it's the prepared entanglement that they have beforehand. So like, if you look at a non-local game that has classical questions, yeah, because you want to, like, I mean, you could vary it, but you want to look at like particular strategies one at a time, see how they do, sort of thing, right?
You can vary it to the same extent as you can vary PAs and QBs. This is essentially.
Yeah, like you look at what kind of data can you get from those things, what kind of correlation matrices can you get from those things, right? And it's sort of similar. You can get correlation matrices. They're slightly horrendous, but they're not as horrendous as they could be.
So one thing you can tell us, and I assume you will tell us, is what's the rule?
Yeah.
We're trying to win the game.
Yeah, we're trying to win the game, so we need certain rules, right? So there's some sort of rule function, and that's kind of the tricky thing. Is it's certainly a bit of a pain to describe what it is. So maybe I'll say it in words. Sure. Okay. Well, I mean, it's not that bad in words, but you sort of assume that only certain states are going to be sent by the referee. So there's a fixed collection of states that the referee is going to send, each with some sort of probability, right? And then there's a particular set of rules for each state. So like if this state was sent, then these answers are allowed and these ones are not, sort of thing.
And that's known to the players.
Yes, that's known to the players, although it's certainly more complicated than the classical case. But yeah, right. But of course now, I mean, yeah.
Because the fees are like X, Y.
Yeah. But now it's somehow even worse because now at least in the XY case, when Alice gets question X, Alice can say, okay, I got question X. Well, when you get this fee, you have no clue what it is, right? So you got to have something that actually works all the time, right? So, yeah. Okay, yeah, so you get, how are we doing here? I realize there's a clock over there. So you get some sort of correlation matrix, right? And does anyone want me to actually write it down or? Okay.
Just one more question.
Yeah.
If we compute the probability of Alice giving the answer A, after the condition that the question was phi,
You're saying is there a well-defined marginal? Yeah, because you essentially are summing over B, right? And the QBs are a P of M.
but it should also involve only the part of phi which sits in the Alice's favor.
Oh, I see what you're saying. So that would be probably, okay, I hadn't thought about that. It's probably the partial trace or something like that, right? You trace out the other space.
Otherwise, it would not make operation sense.
Yep, that's very true. Yeah.
When you view it as a density matrix.
Right. Okay.
Vector.
Sweet. Okay. Okay, yeah, so you get some sort of correlation matrix X. Let's put it at that. And what exactly does it involve without writing it down? Because, our eyes might hurt from that. It involves all the blocks of each of these PAs and QBs, right? And basically how they interact with chi and then how that interproducts with chi. So it's some sort of nasty generalization of the classical setting. It's just you have a lot more entries to deal with. And so now, instead of that, so when you look at classical input, classical output correlations, you have something that's in R to the n squared, m squared, where you have n questions, m answers. Instead, here, this thing is in something slightly more horrendous. So it's in a bunch of copies of mn, tensor mn. And I mean, you could just write this as mn squared instead, but that's maybe a convenient picture to have.
That's an infinite tensor product?
Sorry, it's a Cartesian product of n copies of this tensor product. Yeah, although this tensor product doesn't really matter. Like you could just say it's mn squared and then m times. That would be fine as well. But when you get that many indices, it's kind of sometimes easier to parse things that way. At least that's what I found. But yeah. Okay, and then maybe I should say, yeah, okay. Sorry, still getting used to these. Okay. So just to sort of, before we actually get to the whole quantum homomorphism thing, just to point out the parallels to the classical setting, you still have notions of yeah, what's up?
X should be built out of P of AB5, right?
Yes, unfortunately, X keeps track of a little bit more than that. Well, because it kind of has to keep track of P of AB5 for every possible phi. Not just the ones that the referee is sending in the game, right? And so in particular, it's got to keep track of all the ones of the form, I guess, like...
When you see the thing that I'm saying, but not to happy about m. Don't you get 2m or something like this?
Like n squared.
Or n squared? Exactly, n squared maybe better.
Okay, so for each, oh yeah, you're right, that is m squared. Okay. Can I reach up there? No, I can't. Okay.
We know it's
You know it's m squared. All right, let's settle on that. Yeah, thank you. Typos abound. Okay. All right, so let me just say that there are notions. So like when you look at classical question, classical answer, non-local games, you have notions of local correlations, quantum correlations, QA correlations, QC correlations, and there are notions of those here. So there's notions of loc, Q, QA, QC. I'm not picking on QS for those who like the quantum spatial. It's there too, but since with graph homomorphism it's a synchronous or it's going to be some sort of synchronous game, the QS doesn't actually matter, although that's not at all trivial. But and then just someone wants notation. We could denote these by like quantum to classical. That's what Q sub or QC here means, not to be confused with this one, which is quantum commuting. And then you could even incorporate in there that your question register space is size n, and then your answers, there are m of them possible, right? And you have your your usual containments and stuff like that. Yeah. And then maybe something else I can say. So your sort of characterizations of these are very similar. So like loc would occur exactly when you can arrange for the all of the blocks of the PAs to commute with each other and all the blocks of the QBs to commute with each other. So in other words, what's generated is something that's just commutative. So that if you can arrange for that, that's exactly when your correlation matrix is a local one. And then quantum would be when, okay, so instead of having this H up in the top left here, you'd have it as a tensor product of two finite dimensional pieces. And Alice's PAs would only act on the first part, and Bob's would only act on the second part. And then QA is just, as large and grotesque as this X is, it's still in finite dimensional space. And so QA would be anything that's pointwise limits of things from Q. And your usual containments and all that stuff work in the exact same way. Okay, yeah.
This framework that you presented, you can use it also to study classical to quantum. It's kind of symmetric.
There's a way to, so it's not going to quite be this, but there's a way to talk about classical to quantum. So classical to quantum, what you'd be doing is, okay, let's be careful here. So this is like having, so one way to think of this sort of setup is for each of the players, you have a unital completely positive map from the diagonal on the number of answers into basically wherever their POVM lives, right? That sort of thing, right? For classical to quantum, let me be careful here. Fact check me if need be, but it should be a UCP map from a matrix algebra and then back into a diagonal tensor, whatever extra ancilla you have. Yeah, so there is a way to do it, and there's definitely interesting stuff there. It's just I wanted to simplify things a little bit, yeah. But because you can see this already gets really messy, or at least it can. Yeah. All right. Any other questions? How do we feel so far? Okay. All right. Good. Okay. One thing that's really nice. You can always use PVMs instead of POVMs. So there are nice dilations in this context, and these this way of dilating, one of these kind of POVMs to a PVM in the correct space, it actually preserves finite dimensionality if you have it in the first place. So that's quite nice. And so yeah, in particular, you can deal with all of this using projection valued measures instead. And then what else do I want to say? I guess we could talk a little bit about synchronicity, and then we can get to the actual graph game. So the question is, once you have all this mess, what does synchronicity even look like anymore, right? And actually, maybe before I get that, you might wonder, how do the classical correlation sets sit inside of here? And actually, they sit inside very nicely. It's essentially along the diagonal. So if you're looking at, so T here is any of low Q, QS, QA, QC, whichever one is your favorite. And you want to look at this set of correlations with classical questions, classical answers. It's actually sitting inside of the quantum to classical version, essentially, in sort of the diagonal. So like if you have your P of AB given XY, or let's say P of AB given IJ, let's do it that way. Then your correlation matrix, which has too many indices, right? So that's how many indices would have, but most of them don't really matter, right? Because the only thing that shows up is when, when K is equal to I and when J is equal to L, and then in that case you get exactly this thing. So it's, let's see, it's affinely homeomorphic to that subset. And then also there's a compression going down, a nice continuous compression going down from the larger one. And that's really the idea of just taking your POVMs or PVMs or whatever and just compressing to the diagonal. It's a nice, completely positive map. Okay. All right. Good. Okay. Synchronicity. There are a few forms of synchronicity, so like what Yvonne and Ludmilla and Jason will talk about on Thursday. As far as I can tell, it differs slightly than what from what I'm going to be talking about right now. But the idea, you can actually still say it in terms of sort of probabilities, but the idea is that if your input state that the referee gave you is the maximally entangled Bell state, right? So some of the EI tensor EIs and then normalized, right? If that's the one that's sent to the players, you can think of this as some sort of nice mixture of, like, morally speaking, the mixture of like all the cases where, they're receiving the same question classically, right? And when you receive the same question classically, you're supposed to respond with distinct answer, or sorry, you're supposed to respond with identical answers. There we go. And so in this sort of mixture, what you actually want is this probability is 0 if A is not equal to B. And that's really all the condition is. So this is some sort of like quantum version of synchronicity for classical correlations. Okay. And then, you can write something down in terms of the actual correlation matrix. There's some sort of nice relation. But what happens then, so this is quite nice, and it's similar, but not, I would say not immediate, but it's similar. But synchronous implies that, okay, so really you can write your X as like some sort of, you've got a trace and you've got all your blocks, but the blocks are only coming from one player, right?
There must be some notion of perfect waiting.
A perfect.
Synchronous is just to think about
Yeah, it's a condition, right? So you'll have certain quantum to classical gains that are synchronous. Yeah, and then I'll get to our, well, yeah, anyway. Yeah, so it looks like this, and your trace, it's as in the classical case, your trace is some sort of nice trace on a C-star algebra or von Neumann algebra, depending on what you want. And then you'll notice that Bob's operators aren't here anymore, and it's, well, they are here, but really you can write everything down with Alice's. Yeah.
I didn't get that. Is synchronous the same as saying phi is exactly this, or is it just an example of?
Oh, sorry, this is what I mean by synchronous. So your correlation is synchronous if this condition holds. Yeah, my apologies. Okay.
you're in QA, then projections ought to be taken.
Great question. The answer is yes. Yeah, so the usual characterizations of where your projections live, well, really, it's the blocks of your projections, but where they live is the same idea. So for QC, it's just an a tracial C-star algebra. For QA, these projection blocks all can be arranged to live in an ultra power of the hyperfinite 2-1 factor. If it's Q, you can arrange for finite dimensional, and then if it's low, you can arrange for abelian, right? Okay. Yeah. Mm-hmm.
Equivalent to something like having that kind of function for EI tensor EI for all different types separately, or
Yeah. So that classically, that's what would be the case. This is just because the issue is using that condition. How do I want to say this? Using that condition here, it's really only capturing something about the diagonal of your operators. It's is stronger the right word? I'm trying to think about it. No, it's just with the matrix blocks, it actually captures the right thing, right? If you had a classical thing that still satisfied this, then it's okay. It's not, there's nothing new really. But again, that doesn't capture what happens with these POVMs on this like amplified ancilla. Yeah. Okay.
So I'll just say, Sam, that I have a stronger definition of synchronicity that implies this.
Oh,
If anybody's interested.
cool.
We're gonna talk about it next week.
Okay. I'm too bad I'm not here next week. But okay, yeah, I'd be interested to hear about that. Yeah, does it like? Well, you don't have to answer if you don't want to, but does it involve some sort of state like this, or is it something more general than that? Or okay, cool. Yeah, that would be neat. Okay, let's see. We've got 21 minutes left. I'm looking at this definition of this quantum graph homomorphism game. It's a little hairy, but I mean, I'm happy to go through it, but it's depends what people want, or we can talk about what you actually get as a result of it and just say that it exists. Does anyone have a preference?
Maybe you could tell us what it is. I have a preference to hear what it is before I hear what it
Okay. Yeah, that's fine. That's fine. Okay. All right. Okay. So yeah, how do you define this game? You asked for it. No, I'm kidding. All right, so I'm supposed to look at this game where I have this quantum graph and I'm going to some sort of classical graph, right? And I'm supposed to capture, so yeah, I'm supposed to capture the idea of homomorphism. Now, the problem is when you talk about the classical graph homomorphism game, you have actual vertices that you can talk about, right? You can input vertices. And the question is, what on earth does that look like in a quantum graph, right? Because in this sort of formalism, you're going to have unit vectors, and well, how do unit vectors correspond to vertices, or should they even, right? And what really ends up, so this is not the only way to do this, by the way, but this is one way to do this. If you, yeah, let's do it. Okay. So let's say you had a decomposition of M, right? And it was a direct sum of matrix blocks. So a bunch of M DIs, and then you decompose CN, sort of your question space, into the same way. Direct sum of those. Okay. And then you essentially want to start with, and so one thing I should have mentioned with these question states for this sort of game, you really want these different question states that the referee possibly asks to be perfectly distinguishable from each other. And all that really means is that they're orthogonal states, right? And really orthonormal since they're unit vectors. So what I'm going to do is I'm going to essentially start with some sort of nice orthonormal basis for my operator system. And this is all with respect to the Hilbert-Schmidt trace. And so then your question comes up again, like what does that look like for a generic state? And I have no idea. But essentially what we do is we start with, and I should mention this is, probably the last half. All this stuff is in joint work with Mike Brannon, who is not here, and Priyanka, who is here. So we start with an orthonormal basis. Oh, you do want to know? Okay. It's, do you want the title or the year? Or, okay, it's from 2022. Yeah. That's the quantum to classical graph homomorphism game. There, okay, I can remember something at this point of jet lag. All right, so we start with an orthonormal basis of S, right? And this is with respect to the Hilbert-Schmidt trace. And then I gotta have some sort of, these seem like silly requirements, but this is essentially what made it all sort of work. The first one is that if, if we look at these projections onto each of the copies, or on each of these pieces of Cn, right, corresponding to these blocks, so it's a projection onto CDI, then I want this to be part of my basis. But of course, if it's an orthonormal basis, this is not necessarily a norm 1 vector in the correct sense. So you got to normalize it. So that normalization is just to make it a unit vector. It doesn't matter too much. But this thing is in our basis. And then we also want to make sure that this basis contains an orthonormal basis for the commutant of M. So we're still trying to keep track of information about M, right? And then the last thing is that basically anything in F in this basis is really sitting inside one sort of block in this block matrix decomposition, right? So in other words, there exist R and S such that Y is really the same as doing a sort of corner compression of Y. So if you think of this as some sort of like, you've got this multi-matrix decomposition, you got blocks of all different sizes. Each of these elements of our basis can only live in one block. That's really all that this is saying. Yeah. It may very well. Yeah, it probably does. Okay. Yeah. Yeah. Okay. Well, anyway. No, I think you're right. All right. Well, what I said is still correct. It just might be unnecessary. So let's maybe leave it at that. Okay, and then, well, how the heck does that relate to questions for this game? What's that?
Could you repeat that? Okay.
It was temporary, just
Yeah. Yeah. Oh, shoot, I did it. You know what? I apologize. Okay. Okay, let's do that. Okay, so you have to start with, some sort of, so like really the problem is that these are basis elements for S, but you're not getting matrices as inputs, you're getting vectors. And so really the solution is some sort of vectorization map, or really the reverse of a vectorization map. So you go from a vector that's in a tensor product, and you sort of associate it to a matrix. That's really the idea behind getting from vectors to matrices, right? So like if you, trying to think what the best notation for this is. Nah, you know what? Let's just do it this way. So for this game, your input, right? Let's say your inputs are all these vectors, right? And they're going to look kind of, some sort of like horrendous type. You're going to have a bunch of coefficients. You have some sort of tensor product of vectors, right? This is going to be one of your inputs for this game is some sort of tensor product vector. But it's such that this sort of reverse of the vectorization, right? So if you replace VP tensor VQ with VP VQ star, so this rank 1 operator, this thing, which I'm going to call capital Y alpha, this thing is now some element of f. So I've basically taken the vectorizations of each of the things from f, right? And those are my inputs. And then the rules are, after all that mess, thankfully, the rules are actually quite simple. Okay, so there's really, if you think about the graph homomorphism game, there's really two rules in it, right? There's the adjacency relation, or the adjacency rule, and the synchronicity rule, right? And we're going to essentially get that, but our synchronicity is going to be a little bit stronger here. It's going to almost be like a synchronicity with respect to m prime, right? So the first is the adjacency. So for the adjacency, well, these are elements of our orthonormal basis f. So let's say this, y alpha wasn't actually, part of our orthonormal basis for m prime, in which case it's actually going to be orthogonal to m prime. Then the answers A and B have to satisfy that they're actually adjacent in the target graph. And the idea of this is that if you're orthogonal to m prime, if you think about this in a classical graph operator system, if you're orthogonal to the diagonal, but you're in the graph operator system, that means you're talking about an adjacency, right? So this is really saying like, okay, if I started with an edge in some sort of weird sense, then I end with an edge, right? That's really what we're getting at. And then the other piece is if you're on the commutant of m, well, that's going to be the idea of if you're, if the players receive the same vertex, right? But it's with respect to the quantum vertex set. And so then that's our sort of synchronicity condition, but it's a bit stronger than synchronicity depending on what m prime is. So if this y alpha, if this basis element is in m prime, then you need to have a equals b, right? And so there's our synchronicity. Okay? And there, that's the game. That'll do it. Okay.
So in terms of the right-hand board, we have EAB given P.
Yeah.
So in this case, the P is the vector.
Yes.
The vectorization it's the top thing.
Yeah.
Okay.
Yeah, that's absolutely right. Yeah, and so then perfect strategies would mean, okay, no matter what input vector you're getting from those inputs, the probability that you give correct answers is 1, right? Or the probability that you give incorrect answers is 0. Right? So that's what we mean by winning. And then let me actually describe what it means if you win this game. And then we'll probably have maybe a bit of time for questions, which is good. Oh, that's a great question. Yeah, this looks horribly basis dependent, right? Because there are probably lots of choices of this kind of basis, right? Once you write down the condition for winning strategies, it turns out that part is not basis dependent. So as a result, whichever one you chose, you might get a different game, but winning strategies look the same. For approximate winning strategies, I actually have no idea, and that would be maybe interesting or maybe painful to look at. Is this basis independent for like value or something like that, right? Yeah, I don't know. What's that?
Probably both. Interesting, I think.
Yes, no, I can promise you that you're right. Okay. All right, so for this game, which, here, I'm gonna get rid of this stuff. I want a bit more space than that. For this game that I did not actually give a name for, so let me give a name for it right now, which will hopefully be very intuitive. I'm gonna call it HOM of my quantum graph into G. The following things are equivalent. So, okay. The first is that there's, and I'll say it for winning QC strategies, but then you can sort of port it to the correct statement for QA and Q and log based on what the extra algebra is. So there's a winning, sure. Would you prefer that word? Okay. Sorry, I conflate the two very often. So there's a winning Q, or there we go, see? A perfect QC strategy for this game. And then The second one is that so this is really keeping track of what this PVM actually does. All right, so I guess if we have that G, let's keep things consistent. Let's say G is M vertices, right? And so then I got a PVM, and it's really based on all our formalism. It's in like Mn of something, but actually because M is our quantum vertex set, it doesn't just live in Mn of something. It lives in M tensor something, so a little bit more restrictive. And it's M tensor N for some tracial von Neumann algebra N, and that's your extra piece, right? Okay, and then there's, of course, conditions on this PVM. So, okay, so what do I want? So if I look at the piece of S that's orthogonal to M prime, pardon me, so like sort of the off-diagonal piece, right? And if I tensor this with 1, just to make the spaces match, in that case, essentially I'm trying to capture the idea that I should get something that's, AB should be adjacent in G. And so if they're not, then this product is 0. Okay. All right. And then actually there's another condition on the commutant, but because these things live in M tensor N, that condition is automatic anyway, from the fact that they're going to commute with those things and that PB is 0 if A is not equal to B. Okay. And then the other thing, so one last condition, and then can get to some questions, is that, and you do have to be careful about this, but there's at least a way to come up with a CP-TP map, okay? And where is it actually going? So this is a little bit easier to describe if N is finite dimensional, but if it's infinite dimensional, then really, there's something going on with the pre-dual of this von Neumann algebra. And this is going into the diagonal algebra over the vertices, and it's got some sort of Choi-Krauss representation. And then the other thing that happens is you actually have this sort of push-forward condition like before. Oh gosh, okay. There's not enough space here. All right. So it pushes forward the two different pieces. So if you take, the part of S that's orthogonal to M prime, and you do the push forward of that along this channel, then this is sitting inside of the part of the graph operator system in the target that's off diagonal, right? Like that. So it's moving adjacency to adjacency, like sort of, and it moves there's a push forward of the commutant to the commutant. Yeah, that's a great question. So if N is finite dimensional, right, then there's no problem, right, because this is just finite dimensional stuff. Okay. So then what the heck is happening in the infinite dimensional case? Yeah. Well, in the infinite dimensional case, what happens is that you can arrange, so these PAs, they really give some sort of UCP map, right? Going from the diagonal algebra over the vertices of G, right, into M tensor N. Okay, but it turns out that map is actually going to be normal in this case. And so it's actually the, so there's actually like sort of a, like it's an adjoint of something, right? And that's where this CP-TP map is coming from. And so then, you have to be careful, right? So like if you think of N inside of B of H, you can identify the pre-dual in terms of something inside of the trace class, right? And that's actually kind of important since, of course, this is talking about trace preserving, right? So you need to actually be able to take the trace, right? And so the answer is essentially these depend on how you represent N. right? So again, there's probably absolutely no uniqueness about these FIs, right? But you still get this sort of push forward condition. And I should say this last part is, should push into the diagonal. I always mess that up. Okay, there we go. Okay.
So I think the UCP map going the other way makes sense perfectly, right? And then
Yeah.
You can write so these FI for the UCP map using like Hilbert model version of style spring dilation.
Yes. Yeah.
Then you can take that as FI of FI star.
Okay. Yeah. 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 And actually, I mean, there's some papers where if they look at the infinite dimensional version of CPTP maps, what they're really referring to is that you have a normal UCP map and then use, you know, like Choi-Krause on that. Yeah. But yeah, care is required. Okay. Yeah. So maybe, you know, I can say something about where this goes from here, since we're almost out of time. But you can, if you take G to be a complete graph, right, then you can actually talk about quantum chromatic numbers of quantum graphs. And that's something that's gotten some traction in the literature. So like in this paper, we computed, you know, quantum chromatic numbers for quantum complete graph or just complete graphs of any kind. And it matches up with the dimension of your quantum vertex set, which is quite nice. But then you get this sort of weird thing where if your quantum vertex set is not abelian, then actually the classical chromatic number is infinity. In other words, you can't classically color a, you know, bona fide quantum graph, which is sort of confirms, you know, the idea. But then you can ask questions like, well, okay, how universal is this kind of sort of coloring game, right? And the reason I ask this is that if you look at classical question, classical answer, synchronous non-local games, well, each of those is equivalent to a coloring game. In particular, it's equivalent to a 3 coloring game. Is there some sort of way that's true for like quantum to classical games? I don't know, but that would be an interesting question to know. And another one would even be like, what's the complexity of, you know, deciding if the T chromatic number of a quantum graph is less than or equal to something? And I'm not sure if we even know the answer for that for classical graphs when K is like 4. I'm not even sure if we know the complexity of that. For 3 we do, but for 4 I don't think we know. And then, you know, you could also try to come up with the other sort of parameters like clique number and independence number, right? And do those behave nicely, right? Like classically, clique number and independence number also describe all synchronous non-local games. Does that happen here? Right, so that's another thing you could think about as well. Yeah. It's 11:30. I'll stop talking. Yeah.
How important is it that the referee sends only finite states?
Sorry, say that again.
How important is it that the referee sends only finite states?
Well, again, they got to be perfectly distinguishable. And once they have to be perfectly distinguishable, then you're really looking at an orthonormal set. But since all your questions are coming from CN, tensor CN, it's kind of like shoehorned that it has to be a finite set of questions, right? Yeah, that definitely is part of the definition. I apologize, yeah. But yeah, typically you have to have them be perfectly distinguishable if you want a chance of actually winning. Yeah, so it kind of collapses pretty quickly if, yeah.
Is this version just that definition of synchronous simply that definition?
Like down here? If you have if you have a perfect strategy for this homomorphism game, then you actually get that condition up there. Yeah.
Oh yeah, because of course, yeah, that's about the somehow living in slightly different definitions because they're referred to.
Yeah, and this one depends on certain block sizes, right? But actually, we showed how the blocks were decomposed for synchronicity. That doesn't actually affect things. Like if you have it with respect to one block decomposition, you have it with respect to that one. Yeah.
the whole MN, so then it will be the same.
Yes, yeah. Yeah.
So, suppose it is just one block.
Sure.
So you have some kind of, let's say, you have a projection on this operating system or whatever it is, space, right? There is. So my question is, can you play the same game with the same success with just one state? Maybe if you have a projection right by the right. Because it contains everything that
Oh, I see what you're saying. Yeah, so you're asking like, okay, so instead of unit vectors, can you put it in like a single projection? Yeah, I think you can. Yeah, like the way we did it was with unit vectors, and again, it's like which flavor do you prefer? But yeah, you could absolutely, if you know the probabilities ahead of time as to like the probability that the referee sends a certain.
So the probability you're interested in perfect chapter is right.
Yeah.
So then the probabilities will not matter.
That's true. That's absolutely true. Yeah. So what you would do is you essentially take some sort of like, you're essentially trying to capture all the unit vectors at once. And then your rule function is really, what is it? Some sort of like join preserving map on the projection lattice. But that's if you're taking projections as your questions. Yeah. Oh, sure. Yeah. So, I mean, yeah, you could take a bunch of little projections. Sure. Yeah. So you could do that as well. And that might actually be simpler than whatever I wrote down here. But yeah.
Let's look at it. So in this particular example, what would be the rule?
If you have this state,
I have my single state, and now, okay, what are the rules for this particular case?
There's only one question.
There's only one question. So what's the rule regarding that?
yeah.
Well, I mean, I think what you're getting at is like, okay, so you have your projection for the Komiton, you have your projection for the rest, right? Yeah, like, so, okay, yeah, so.
Just you not answer with the same AA, probability AA given the state, the question is 0.
If you have the projection corresponding to the off-diagonal piece, right?
Never been the graph.
No, it is in the question. The question is the graph.
No, the output graph.
The output graph is supposed to be just the coloring game. Or the complete my question. for the coloring.
Right, yeah. But you could tweak that a bit, right, for, yeah.
But I mean, if you have an arbitrary graph, it's the same, right? A adjacent to B, given the state that you're asking should be 0, probably 0. And not adjacent, given the question should be 0. That's it. Yeah. So the thing is, you instead of asking many questions, just one question which contains the whole graph of it.
He's asking all the questions at once. Like all the, like, okay, I mean, that sounds silly, but that's kind of how it works, right? You're asking all the adjacency questions at once, essentially, right? Yeah.
So what would be the classical picture?
Yeah, you're inputting the adjacency state that is corresponding to adjacency matrix of the first graph. Taking all the sums of all the EX tensor dy, where X is adjacent to Y, dividing by the number of edges, square rooted. And that's your question. And you want this question, if you have this question, to present something that has be a adjacent, not adjacent.
Maybe it does make sense, because I think that the difference is that, you see, that somehow that, I mean, it's not like Alice will get the whole question, she just gets the partial trace.
Right, yeah.
Bit weird, the more you think about it.
There's this notion of the chromatic number of an operator system, maximum number of vectors, so that if you do psi I, psi j star perpendicular to the operator system. I wonder if that's the largest number for which you have perfect strategy.
I think you mean smallest, do you not? Because I mean, if you have one for one size, you have. Yeah. I believe it is. I believe that's the case when you're looking at a non-commutative graph, right? So when your M is like just the whole matrix algebra, right? I believe then, yeah, then that would fall exactly into this sort of framework.
To this notion.
Yeah, now there are other ones where you have to be a little bit careful. So like, for example, I mean, this is kind of a classic issue in the literature, but the entanglement-assisted homomorphism, right? That one gets tricky, right? Because it's like, well, how exactly are you assisting it? And I know Stalky's definition of it, at least as far as I know, I think it's still open whether or not that actually is the same thing as quantum homomorphism in the context of a non-local game, but they're certainly close. Anyone else?
Should we thank Sam again?